Hey everyone, and welcome back to the channel. Imagine looking back in time, not just thousands or millions, but billions of years. Imagine peeking into the cosmic dawn when the universe was barely a toddler, a mere fraction of its current age. For decades, our telescopes have shown us a blurry, faint impression of this era, suggesting a period of cosmic calm, a time before the grand structures we see today had truly taken shape. We called it the Dark Ages, a primordial soup slowly cooling, slowly coalescing, patiently waiting for the first stars and galaxies to ignite. Our best models, built on decades of painstaking observation and theoretical brilliance, the very foundation of our understanding of the Big Bang, painted a clear picture of what that early universe should look like. But then we launched the James Webb Space Telescope, humanity's most ambitious eye on the cosmos. And what it showed us wasn't just unexpected, it was utterly, profoundly baffling. It showed us a universe that, according to our most cherished theories, shouldn't exist. For nearly a century, our understanding of the universe has been anchored to the Big Bang theory, elegantly described by the Lambda-CDM model. This model posits that our universe began with an incomprehensibly hot, dense state, expanding and cooling over 13.8 billion years, to become the vast, structured cosmos we inhabit today. A crucial part of this model is the timeline of structure formation. After the Big Bang, there was a period of rapid expansion, then a cooling, followed by the Dark Ages, a time where the universe was filled primarily with hydrogen and helium gas, with no stars or galaxies yet formed. Gravity, that relentless sculptor of the cosmos, would then begin its slow, arduous work, pulling together pockets of this gas, eventually forming the very first, small, nascent stars, and then, much later, tiny, irregular proto-galaxies. These early galaxies, we believed, would be relatively small, sparse, and chemically pristine, slowly growing over billions of years through mergers and accretion to form the magnificent spirals and ellipticals we observe in the local universe. This was the expected narrative. This was the cosmic blueprint. Our previous generation of space telescopes, like Hubble, pushed the boundaries of this cosmic archaeology, giving us tantalizing glimpses of these early structures. We saw faint smudges, distant light that had traveled for over 13 billion years, hinting at a bustling early universe. But Hubble, being primarily an optical telescope, struggled to penetrate the veil of redshifted light. As the universe expands, light from distant objects gets stretched, moving from visible light wavelengths into the infrared spectrum. This is where the James Webb Space Telescope comes in. Equipped with an enormous, gold-plated mirror and instruments specifically designed to detect infrared light, JWST was built to peer through this cosmic redshift, to truly see the universe as it was just after its birth. It was designed to find those first, small, pristine galaxies, the expected cosmic infants. What JWST found, however, was anything but infant-like. Almost immediately after its first images were released, a cascade of discoveries began to pour in, each one more astonishing than the last. Astronomers began to identify galaxies at redshifts far higher than anticipated redshift 10, redshift 12, even redshift 16. What does a redshift of 10 or 12 mean? It means we are seeing these objects as they were just 400 to 300 million years after the Big Bang, when the universe was less than 3% of its current age. We expected to see sparse, tiny, struggling systems. Instead, JWST revealed a startling abundance of bright, massive, and seemingly mature galaxies. Take, for instance, a galaxy nicknamed Glass Z13, one of the earliest confirmed galaxies. At redshift 13.1, we see it as it was only 325 million years after the Big Bang. But instead of a small collection of first-generation stars, Glass Z13 appears to be a compact, surprisingly luminous galaxy, already containing billions of stars. Or consider JADES, GS, Z13-0, another confirmed galaxy seen 330 million years after the Big Bang, also remarkably bright and massive. Then there's CERS 2112, observed just 290 million years post-Big Bang, already a well-established system. And the list goes on. JWST has identified a growing population of these impossible galaxies, some of them showing signs of complex chemical enrichment, indicating multiple generations of stars have already lived and died, enriching the interstellar medium with heavier elements, a process that takes time. This is where the profound mystery truly deepens, where the universe starts to look like something that shouldn't exist. How could these galaxies have formed so quickly? In the standard Lambda-CDM model, the early universe simply didn't provide enough time or the right conditions for such massive structures to coalesce. Gravity, while powerful, isn't instantaneous. It takes billions of years for gas and dark matter to accumulate into the vast halos required to host such large galaxies. Star formation, too, is a process with inherent limits. While the very first stars, population III stars, might have been massive and short-lived, even their formation and subsequent death to enrich the cosmic gas takes time. For a galaxy to accumulate billions of stars, and to show signs of multiple stellar generations and chemical enrichment within a mere few 100 million years seems to defy the cosmic clock. Let's break down the timeline challenge. Imagine trying to build a skyscraper in a week. You'd need materials to appear instantly, workers to build at superhuman speed, and foundations to settle overnight. In the early universe, the materials hydrogen and helium gas, dark matter, were dispersed. The workers' gravity, star formation processes were operating under known physical laws. The construction time was incredibly short. Form a galaxy like the one's JWST is seeing already